Welcome to lesson 4, example number 1. And they are asking to design a beam given a 2,000 pounds equivalent distributed load, and then pounds per linear foot, that is. And then the span is 24 foot. They also say that it's A36 steel, which has a yield stress of 36 KSI, and then it has full lateral support. And that means they do a decent job, or good job explaining it. But this, and we know we're going to have all positive moment. This is simply supported beam. It's going to be a completely positive moment. The beam's going to go like so. That's all positive. Typically, when you have full support, that means, well, we had a positive moment, so we know that the bottom flange, or the bottom half, is going to be in tension, but we can say bottom flange is going to be in tension. Won't write it tension. And the top is going to be in compression. Alright, close enough. And the compression flange will buckle, just like I don't think they've done that yet, but knowing what you know, if you have, let's say, just a bar, let's say, like a reinforcing bar, and it's straight, but you compress it, you push it down on it, it's going to buckle out here like that. And it will break, just like a pencil would, I guess, is how I always explain it. But if you have a pencil and you restrain it laterally, let's say you have a pencil and you put your hand around it, you have a bunch of fingers, and you put both hands around it, it will actually, you can use all the compression strength of that pencil because it is laterally supported. So you'll be able to you have a higher compression load here since you are supporting it laterally. I hope that makes sense. And if you don't support it, then it will want to what we call buckling. It will want to do that. And they'll go over this. I think we go over a little bit more later on in this chapter, the buckling principles. All right, so in this we are assuming that it is laterally 100% full lateral support. All right, so we take a look at this. We could solve for the reactions and do shear moment diagrams, or we know it's a distributed load. We can just do M max equals WL squared over 8. Let's go ahead and solve for that. 2,000 pounds per linear foot times 24 foot squared over 8 gives you 2,000 times 24 squared divided by 8 is 144,000 foot-pounds. Alright, and let's just go ahead and write another equation down here. We know that the stress in bending, and this is actual stress, is going to be M over S. And we know M, we just got M. We do not know S, and we do not know that's going to be a function of what S is. So depending on what we choose for our section is going to give us our S. So what we could do is go ahead and plug in right here our allowable. And if we plug in our allowable, then that will give us our S min. And for FB, we know, if you look earlier, that when you're doing what's called allowable stress design, and they do a good job of saying what allowable stress design is. And there are other types of design, load factor design, and there's also LRFD, which is, well, load factor design is called LFD, and then there's load and resistance factor design, which is LRFD. And what you do on those is, LRFD is you hit both sides. And once again, you can just ignore me if you don't want to hear this stuff. It might be confusing. But you have LFD, which is load factor design, which I like to look at it. This is just general principles, and it gets a little bit more complicated than what I'm putting off here. But in general, load factor is you hit the loads with a factor. So you'll have your capacity, let's say let's say capacity or resistance, whatever you want to call it, and that needs to be greater than your load. And that's typically what you'll come out as. And then this will factor the load. So for instance, you can get like you'll see this type of stuff, 1.4 dead load plus 1.67 live load. I'm making these up. Plus, this could be strength 1 is what they call this type of load. Plus, let's say 1.4 wind load or roof load or whatever you want to look at, snow load. They have different things, and you can look at those, and ASCE7 is where you come up with a lot of those load factors. And so but you won't do anything to capacity. You kind of leave it as it is generally. That's load factor design. And then you have LRFD, which is called load and resistance factor design. And what you'll do is you actually hit both sides. Capacity. So, and this could also name as the resistance. You can say this is resistance and this is load. And you hit this, you'll have the same type of stuff. You'll have these type of loads, except some of them will be less than those, because obviously you're doing things over here as well to reduce capacity, but you're increasing loads. Well, typically increasing. Sometimes you don't, but you're getting to a more, I guess, fine pencil. You're sharpening your pencil on the loads to get a more realistic situation. And then you're looking at your capacity and what actually happens with capacity. For instance, what we're doing over here is you're saying, okay, and this is called allowable stress design, ASD. Stress, so let's put allowable stress there. And what you do in allowable stress is load is, of course, less than your capacity, or your actual stress needs to be less than your allowable stress, or your resistance needs to be greater. A lot of different words you can use. But you're going to actually hit your capacity. And in this case, if you look earlier in the chapter, it explains that, your stress and bending actually equals, they put this first, is 0.66 Fy if you have these certain conditions. So you're actually going to come out with 24 KSI, which is 24,000 PSI. And then in shear, so if you're dealing with shear, you will actually look at, and it's usually 0.4, if I remember correctly, Fy. So you're going to come out, if you have 36 KSI, it's what, times 14.4. Or sometimes people say 15 KSI, or maybe they'll use 14. It's kind of just around there. 14.5. I use 14.4. I just put it in there. And so this is your new allowables, and you factored your capacity. This is your yield stress, and you factored that yield stress. So you're reducing your capacity in ASD only. And here, you're reducing your capacity. In LRFD, you're reducing your capacity, and you're increasing or modifying your load to deal with a real-life situation. And in this situation, you're not looking at, well, sometimes you can have, different wind loads. In summer, you're not going to get wind plus, snow or stuff like that. You might get your max temperature changes in your summer, but you're not going to get your snow. So they want to, this LRFD is probably the most accurate, you could say, because this is kind of where everything's going to, is LRFD. And capacity is looking at your material and how accurate that material is. For instance, if you have steel, you're going to have higher stuff. If you have wood, the load factors are going to be they're going to decrease your capacity more because it's more uncertain. So the more uncertainty you have in this capacity, the more you have to decrease it. And there's actually certain tests when you go into LRFD where you can, especially with soils, and that's it's a work in progress, but the soils are, there's a lot of unknowns in the soil. So if you don't do any tests, this load, it could be zero point 0.4 of your soil capacity if you don't do any tests. But if you do tests and you have pretty darn accurate data, you can go, 0.7 capacity. And if you think about it, that's about doubling. So sometimes it's economically feasible to do some expensive tests because you can have half the piles if you have really long piles or something like that. So I hope that wasn't too confusing. That was just a quick overview of that, and I'll do some more videos in the future about the different types of design and how those fit in. But right now we are right here, and we said that the force of bending equals 0.66 Fy equals, we plug 60 or 36 in there, and we get 24,000. Let's stick with PSI. All right, 24,000 PSI. So let's go ahead and throw that in there. Equals 24, and that's our max PSI, our max allowable, and that will give us our min, and then we have to figure out, we have to get something bigger than this S min. And S min is going to be 144,000 divided by 24,000, which is 6. S min equals, oh shoot, now I did something that's common here. I didn't change this into inches. That's why it's incredibly important to follow your units through. You'll catch a lot of your mistakes, which I just did. All right, so we want to get rid of foot. We put foot on the bottom. We say it's equal to 12 inches on top. And we recalculate 144,000 times 12 divided by 24,000 equals 72 inches cubed. And that's what we need to design for. And the easiest way to do this is to go, you'll see that your steel book, and it has allowable stress design selection table. And there's 3 different ways, and I would go through all the 3 different ways, the methods that they have put down there. And the best way, and the most economical, if you have a simple design that's completely laterally supported, is to go use these allowable stress design selection tables on. They're out of your steel manual, but they're posted on page 64 of your study guide. And they have, in bold, they'll have the lightest section, the most economical section. So you just kind of go down. And as long as you don't have any height requirements, you can go down and say, okay, where am I at? I need 72. And you say, okay, you go to this aisle, and then you go up, and you'll say, look, and you'll see that the most economical section is W21 times 44. And it has an S of 81.6, and that should be inches to the third. All right, so that was pretty simple. And as you can see, it also, you can design it, these tables, using your maximum moment as well. And it said the maximum moment is 162 foot kips, or kip foot, depending on how you like to say it. So that's our answer right there. We just designed a beam, and it's going to be a W21 by 44. And you really could go back and you could check your shear, but I'm telling you right now, it's going to be all right. Typically, these beams will control in moment or bending 99% of the time, unless you have certain circumstances where it's a really short beam, so you won't have too much moment. Then you need to look at shear. But for this case, we'll just assume that's good and move on. We'll see you in the next video.